Hi, I'm Mike Ryan. I'm a security consultant with ISEC Partners, and I have a lot to get into, so I'll just get right into it. So here's an outline of the talk. I'll tell you what is Bluetooth Low Energy, give you an overview of the protocol, talk about the techniques I've developed for sniffing it, touch on the security or lack thereof, and finally briefly discuss injection. So what...
Has 50 slides, so I'm just going to pull like a full Alex Stamos and just talk super fast.
Yeah, if you want me to slow down, I'm sorry, I can't. There's only one speed. So, what is Bluetooth Low Energy? Well, actually, it's not anymore. It's called Bluetooth Smart. That's what happens when you let marketers get a hold of your protocol. So, it is a new modulation mode and link layer for low power devices. As compared to classic Bluetooth, it's physically incompatible. Bluetooth Smart devices cannot talk to classic Bluetooth devices and vice versa. That's because at the PHY layer and the link layer, they're pretty much completely different. However, they do reuse some of the higher level protocols such as L2CAP and the attribute protocol, which makes analyzing it a little bit nicer. It was introduced back in 2010 as a part of the Bluetooth 4.0 spec. Sometimes you'll hear it referred to incorrectly as Bluetooth 4.0. Bluetooth Smart is a subset of Bluetooth 4. Bluetooth 4 encompasses all of the existing Bluetooth technology as well. Also known as BTLE, I am totally inconsistent because depending on who I'm talking to, I'll call it Bluetooth Low Energy or Bluetooth Smart. So if I say anything, they're all the same. Where do you find it? Mostly these days in high-end smartphones and sports and fitness devices like the Fitbit. So if you've got an Apple iDevice made in the last 2 years, you probably have it. If you've got a couple Android manufacturers have been shipping the hardware, and as of the 4.3 update, they have software support for that now. Interestingly, I've seen like at least 4 or 5 different manufacturers making Bluetooth-enabled door locks, and a couple of upcoming medical devices, like this blood glucose monitor that I found on the Bluetooth SIG's website. That just doesn't sound like a good idea to me, but hey, what do I know? As far as the numbers go, in the first half of the year, there's 186% year-over-year growth, 7 million devices shipped, just the first half of the year. So this is pretty much the next big thing in low-power wireless devices, consumer wireless. Also, the Bluetooth SIG, tooting its own horn, suggests that it will be leading the market share in wireless medical devices. Pretty interesting stuff. So, moving on to the protocol itself. This is what the protocol stack looks like. At the bottom, you've got the PHY layer and the link layer. Remember, these are unique to Bluetooth Smart. And above that, you've got L2CAP, AT, and GAT. I don't really have enough time to get into those, so I'll just focus on the PHY layer and the link layer during this talk. So when a, excuse me, when a Bluetooth Smart device transmits, what does it look like? It generates a small amount of modulated RF, and it's modulated using Gaussian frequency shift keying, a simple modulation mode, using 250 kilohertz offset at 1 megabit a second. And it transmits on one of 40 channels in the 2.4 gigahertz spectrum. This is the same spectrum that's used by 802.11, Wi-Fi, some Zigbee, classic Bluetooth. There's a lot of stuff going on in there. One way in which it actually differs from Zigbee and other low-power wireless devices is it actually hops as a matter of course, rather than just hopping to avoid interference. So speaking of hopping, the protocol breaks the spectrum up into 40 channels. 3 of those channels are devoted to advertising. When a device is unconnected, it just sits around on an advertising channel, periodically broadcasting its existence, saying, hey, if you want to connect to me, this is my address, and then a master will issue a connect request. During a connection, it transmits on the 37 data channels, and it hops according to a pretty simple hopping pattern. So during a connection, a master and slave both hop to a channel, the master transmits, the slave transmits, then they wait for a brief period of time, and they hop to the next channel and do the same dance all over again. So the length of time they spend on a specific channel is called the hop interval. This is unique to connections, and it's exchanged by the master to the slave when the connection's established. And the way they find the next channel is they take the current channel, they add a value called the hop increment, and that's it. They just mod 37 so you don't fall off the end of the spectrum. So at the bottom there, I've got an example hop sequence, and our hop increment is 7. So the master and the slave will hop to channel 3, master will transmit, slave will transmit, then they wait for the hop interval, then they hop to 3 plus 7 equals 10, master transmits, slave transmits, wait again, so on and so forth. And they'll complete a cycle of all 37 channels before returning to channel 3, because 37 is prime. And that's pretty much it for the PHY layer. You've got your modulation technique, and you've got your channel hopping sequence. Moving on up to the link layer, this is where we're actually dealing with real data. And if you see the word octet, that means byte. I don't know why networking people call bytes octets, but it's all the same. So every packet starts with a preamble. This is an 8-bit sequence of 010101. This gives the receiving radio a chance to synchronize its bit timing. Following that is an access address. This is a 32-bit value that's unique to every connection. This is what allows the receiving radio to pick up signal from the noise and identify that it's actually a packet that's a part of its connection, rather than just some spurious emission. Following the access address is the protocol data unit. This is where the user data lives. And at the end of it is a simple CRC, which is not calculated the way you would expect. There's a minimum length of 2 bytes in the protocol data unit because every PDU has a 2-byte header that has the length and a flag that tells you whether you're looking at a control packet or user data. And there's also a couple of flags for things like flow control. On top of the link layer, you've got L2 cap and so forth. We just use existing decoders for this because they already exist, and I don't want to re-implement stuff because I'm too busy. This is not a hard problem, so I won't really focus on this during the talk. So to recap, at the bottom you've got the PHY layer, GFSK, yada yada yada. Above that you've got the link layer. Pretty straightforward when you actually look at it. It took the Bluetooth SIG 2,000 pages to get this information to me. So moving on, how do we actually sniff connections? If any of you follow Mike Osman's research, you'll note that sniffing Bluetooth is hard. And this is totally true. However, he was talking about classic basic rate Bluetooth. We're talking about Bluetooth LE, which is a little bit easier. So how do we do that? You start at the bottom and you work your way up. Remember, the PHY layer and the link layer, again, are unique to Bluetooth Smart. So we need to develop techniques for sniffing those. And to do that, I use an Ubertooth. And if you don't know what an Ubertooth is, I've got one up here. I can show you after the talk if you're interested. And I'll talk about it in the next slide a little bit. So we use the Ubertooth to get at the raw RF and turn that RF into bits and link layer packets that then we can pass up to the PC and use all sorts of great stuff to analyze those. So an Ubertooth, here's a block diagram of one. It's really a general purpose RF experimentation platform, but as the name implies, it's aimed to be able to do Bluetooth. It has a reconfigurable radio chip and an ARM microcontroller on it. So on the far left there, connected to the antenna, there's actually a small RF amplifier that just helps us get a little bit better, wow, it's a little early in the morning. Signal strength, thank you. Then connected to that is a CC2400. That's a reconfigurable radio chip, and that handles the PHY layer for us. We tell it what channel to be on, we tell it what modulation parameters to use, and then it just spits bits in our direction. Those bits are handed off to an LPC 1750 series ARM microcontroller. That pretty much does the link layer. That turns the bits into packets. And then finally, we throw those packets down through USB onto the PC where we can process them there. So the PHY layer, to capture it, we just configure the CC2400 to match Bluetooth Smart. We say GFSK, 1 megabit, 250 kilohertz offsets, and then we tune it to the proper channel and say, go, give me bits. And it just shoots bits in our direction. And then we change the channels whenever we're supposed to hop. Remember the hopping pattern I talked about a couple slides ago. And that depends on a couple of values that I'll get into in the next slide or two, how we recover those. And finally, we just take the bits that the CC2400 is spitting out to us. When a Bluetooth Smart device transmits, those bits will actually be the bits transmitted by the Bluetooth device, and we can process them on the microcontroller and turn them into packets that we hand off to the PC. So what information do we actually need to sniff a connection? Well, mainly we need the access address and the channel number. Remember, the access address is at the beginning of every packet. That's how we identify that we're looking at a Bluetooth packet, not some other transmission. And also we need the channel number to know which channel to be on. During a data connection, they hop around. You need to know which channel to be on at a particular instant in time, or if you're on an advertising channel, you just need to tune it to that. So where does the access address come from? On advertising channels, it's always a fixed value, 8089BED6. So you can just sit around on an advertising channel looking for this 32-bit sequence, and when you see it, the next data is probably going to be an advertising packet. On a connection, that value varies. Every connection, in theory, gets a unique value for that, and I'll tell you how we get that in a second. So as far as the channel number goes, remember, we need the hop interval to know how long we sit on a particular channel for, and we also need to know the hop increment. Finally, it's nice to have the CRCinit, which is used to calculate the CRC, so we can filter out false positives and just look for valid data only. So where do these values actually come from? The easiest way to observe them is to observe a connect packet. You sit on an advertising channel, you wait for a master to issue a connect, and you can just pull all 4 of those values right out from the connect packet. So let's just assume that that's how we did it for now. So we've got our access address, all the hop parameters, and our CRC in it. That allows us to move up to the link layer. So we've got the bits coming in off the radio chip. We know the access address, and we want the start of the PDU. So we just look at the bits that are coming in, we start looking at them, and oh, that looks like the start of our access address, a couple more bits from our access address, bingo, 32-bit access address. The data following this is probably our PDU. So that's how we go from raw RF to the start of the PDU. And that's actually a lie, because that's how we used to do it. The way we do it now is that we tell the CC2400, look for this 32-bit value, and give me data when you see it. And that actually gives us nice byte-aligned data that came right over the air, and we don't have to do very much work at all, which is awesome. So we've got our PHY layer, we've got our link layer, we've turned our RF into bits, we've turned those bits into packets. Now what do? We take advantage of existing software. This is a screenshot of some of Wireshark's protocol dissectors. At the very bottom, you can see the Bluetooth L2CAP protocol, and at the very top, you see the Bluetooth attribute protocol. So if we can get our data into Wireshark, we can use these to pull apart our packets. How do you get data into Wireshark? PCAP. Ubertooth BTLE is the command line tool that speaks to Ubertooth, and that handles packets. So all we do is fire up a libpcap and dump some raw packet data out to a file descriptor, slap a PPI header on the beginning of it, the same way the AeroDump NG and Kismet slap a PPI header on top of their non-Ethernet data sources, and we can just stuff it into Wireshark using a couple neat tricks, or just capture to a PCAP file and load it up. And in fact, we do have a DLT for Bluetooth Smart. One of the last times I gave this talk, we did not have that. Now we have a unique identifier for our protocol, which means we can make a public tarball release of our Wireshark plugin very soon now. I'm actually going to try to push that upstream into Wireshark. So yeah, that's pretty nice. So here's some screenshots of Wireshark in action, displaying packets that I sniffed over the air from a Bluetooth device using an Ubertooth. You can see the highlighted field right down here, it's probably hard to see, is requesting the name of a device that I think I have with me. And here is the response, the device saying, oh, I'm a TI BLE sensor tag. Again, these were sniffed over the air using Ubertooth and then loaded up into Wireshark so that you can actually understand what the hell is going on. So the 4 values, if you observe a connect packet, are easy to get. If you don't observe a connect packet, you have to use some special techniques. And realistically, you're probably not going to be sitting around on the correct advertising channel when a connection is established. So Promiscuous Mode allows you to recover those 4 values from already existing connections as they're happening. So I'll tell you the techniques we use to recover them. So recovering an access address from an existing connection, we sit on a data channel and we exploit the fact that empty data packets have a very predictable format. Remember that a master and a slave hop to a channel and they each transmit. Even if they don't have any data to transmit, they have to transmit something. So they transmit an empty data packet. This is a 2-byte header that has a data flag set and a length of 0. So that's a 16-bit value, actually 14 bits, that we can match on looking for these packets. So we just sit around waiting for these predictable packet formats. An example of that is highlighted in green on this slide. And when we see this 16-bit value, we rewind our data stream 32 bits, and we treat that value as a candidate access address. This technique generates a lot of false positives because you're only filtering on 14 or so bits. That means that you're just going to get a lot of random garbage over the air. So we keep a table of all the values that we've observed, and once we've observed a value enough times, we treat that as a candidate access address and move on to the next step, in which we recover the CRCinit. So Bluetooth Smart calculates the CRC a little bit differently than I've ever seen. It uses this long linear feedback shift register here, and when you start calculating your CRC, you fill it with a 24-bit value known as the CRCinit. This value is unique to every connection except for on the advertising channel where it's fixed. So you fill this guy up with your CRCinit, you feed the packet data in 1 bit at a time, and then at the end, you take the value that's in your LFSR and treat that as your CRC. It turns out back in 2007, there was a USENIX WOOT paper about how to reverse this process in the original Bluetooth the original classic Bluetooth protocol. Well, the CRC LFSR here is also fully reversible. You pretty much just turn the arrows around and you can run it backwards. So we can use that technique to recover the CRCinit given a CRC. Well, we've got tons of candidate packets because we've got them filtered on access address. We know their length because we can look in the header, so we know the 24-bit CRC that's at the end. We take that 24-bit CRC, plug it into the reversed CRC LFSR, and run the bits through it backwards, and then at the end we're left with a 24-bit value in our CRC LFSR. That is actually going to be the CRCinit. Again, we've got some false positives, a lot less, but there are still some, so we just use the technique of observing a couple of values, and once we see the value a couple of times, we treat it as our CRCinit. That allows us to move on to recovering the hop interval. This one's actually pretty easy. We sit on a channel and we wait for 2 consecutive data packets. Because 37 is a prime number, every connection must visit every other channel in the hop sequence before returning to the original channel. So if we take the amount of time that it took to receive 2 consecutive packets on a single channel, divide that by 37, that gives us our hop interval in milliseconds. That's it. Finally, recovering the hop increment. This is the part that actually took some thinking. So bear with me for a minute. I'll get into the math on the next slide. We start on data channel 0. We wait until we receive a packet. Then we jump to data channel 1, and we wait until we receive a packet there. And then we can calculate the time difference between receiving packets on data channel 0 and data channel 1. We know the hop interval in units of time, so we can divide that value and calculate how many channels were hopped between 0 and 1. So let's say we go to channel 0, jump to channel 1. In the meantime, the Bluetooth Smart connection may have jumped to channel 5, channel 10, so on and so forth, and eventually came back to channel 1. We know how many channels it took to get there. So using some fancy math, we can write it out like this. 0 plus the hop increment times the number of channels hopped equals 1. We know the number of channels hopped. In fact, we also know that the number of channels hopped is non-zero, so we can calculate its multiplicative inverse. Because 37 is prime, the hop sequence is isomorphic to z sub 37, so the multiplicative inverse is well defined for non-zero values. In fact, Fermat's little theorem gives us a nice closed form for calculating it. Unfortunately, having a closed form doesn't mean it's efficient to calculate it, so we use a lookup table. And therefore, we can calculate the hop increment by using a lookup table for the inverse of channels hopped, and that will just give us the hop increment as an integer. And that's it. So we can follow connections using the techniques I described at the beginning of this section, and this depends on these 4 key values listed here. If we observe the connect packet, we just get them for free. Oh boy, 5 minutes. And if we use our techniques for our promiscuous mode techniques, we can recover them from the connection. That's the only part of this talk that actually took any amount of thinking, so I don't feel bad that I covered this. All right, talking about security a little bit. There is encryption provided by the protocol. It's provided by the link layer. It encrypts and authenticates the protocol data unit using the AES CCM algorithm. There's not a lot to say about this because that's a pretty good algorithm. If you've ever used WPA AES, that's what they're talking about. The problem is in the key exchange protocol. There are a lot of great key exchange protocols out there. The Bluetooth SIG did not use any of them. They invented their own. It's a three-stage process. The pairing method determines the first stage, and there are 3 pairing methods. However, none of the pairing methods provide protection against a passive eavesdropper. That's right. They published a spec with a broken key exchange protocol, and they didn't even say, I'm sorry. But they said, we will fix it eventually. So, the first stage, the master and slave transmit some values, and they want to make sure they agree on a value called the TK, the temporary key. So they transmit these values in green over the air in plain text, the confirm, the rand, P1 and P2. We have these values, and we don't have the temporary key, but we have everything used to calculate the temporary key. In fact, we know some things about the temporary key. It is an integer between 0 and 999,999. That's not a lot of bits of entropy. In fact, we know something else about the temporary key. In just works, that value is always 0. Does anybody want to guess what the worst case scenario is? 1 second to crack. We can do an offline attack against this, but we don't have to. It's so stupid that we can just do it in real time and continue decrypting the connection. And that's it. Using the temporary key, we can decrypt the short-term key. The short-term key, we get the long-term key, and the long-term key is used to encrypt the session keys. So we've got every key used to encrypt our communications. Your key exchange is broken, and it's passive. The only way you can tell is if you look around at the coffee shop and see this guy. One more nail in the coffin. The long-term key is reused between connections. This is great. It's an optimization, and it's good for security. If you pair in a Faraday cage, it's impossible for your attacker to sniff your connection. However, there is a mitigation to that, which is there's an active attack to force repairing that's so damn simple that I didn't even bother to make a slide about it. All you need to know is the MAC address of your target device. And then you can decrypt the data using the long-term key. I won't go into the procedure because it's really simple. And I wrote a tool to do it too. So you can hand this tool a PCAP file that has your pairing exchange, and it will crack the temporary key and decrypt the rest of the PCAP file. Also, if you give it a PCAP file with an encrypted session, it will decrypt that too if you give it the long-term key. Am I affected? Probably. Because this is a protocol error. It's not a specific vendor's implementation problem. There is one exception. Some vendors have implemented their own security on top of GATT. They did not talk to cryptographers when they did so. So to recap, your key exchange is broken and I can decrypt all your communications. And it's passive. Finally, injection. This is quick. It's the same as sniffing, except you turn around all the arrows. You follow the spec. You take your link layer header. Oh, 1 minute. You take your link layer header. You add payload data to it. You hand it off to the Ubertooth, which calculates the CRC, whitens the data, and shoves it out the CC2400. That's a lot harder than it sounds. I don't have time for a demo, but I brought a rubber chicken just in case it failed. So to summarize, our capabilities, we can passively intercept Bluetooth low energy. We have Promiscuous Mode to intercept connections that already exist. We can inject. I wrote some Wireshark plugins to make it a lot easier, and I wrote a tool to crack the TK and decrypt all your data. Here's some software links. I will put this up later. Don't worry about that nano-ECC stuff, but if you want to check it out, go ahead. So anyway, a very special thank you to Mike Osman and Dominic Smill, the coolest guys in the entire world, for doing the Ubertooth project. A whole bunch more other people who helped out. I can't name them all right now because I don't have time. Thank you, USENIX. Thank you, everyone, for coming here. And if you have any questions, I'll take them now. Please come to the mic.
What's your range of being able to intercept packets?
I think everyone heard that. So how far away can we intercept packets? So the Ubertooth is slightly more sensitive than your typical Bluetooth Smart device. Bluetooth Smart, I can probably keep a connection established between here and the projector. This guy will pick up packets from about as far away as that gentleman in the green shirt right there. So about twice as far. So, I don't know, maybe 10 meters? Yeah. It's really low power stuff.
You want to try a demo? There's no other questions.
I really don't want to try a demo right now. I'm restructuring the code.
Yeah, this is Rick. So that was a nice description of Bluetooth Smart. How different is regular Bluetooth than Bluetooth Smart?
Classic Bluetooth is a hell of a lot more complicated than this. We do have a classic Bluetooth sniffer running on Ubertooth. It is probably like 20% of the functionality of this. If you give it some connection parameters that you get from a device that has an established connection, you can follow it pretty effectively as long as it doesn't use adaptive frequency hopping. But I'm not an authority on the matter. You should come join our IRC channel or hit up the mailing list if you want more details about that. And I think, no, so Dominic Spill, the lead on the Ubertooth project, just gave a talk about it at DEF CON, but it was not recorded. It was just in the Wireless Village. So I'll see if I can get him to write a blog post about it.
Okay. Hey, thanks. This is great.
Yep. Any other questions? Got one more.
Oh, we do a lot of this kind of hopping and attacking, defending all the time. I was wondering your fancy math, how difficult it is if I change a lot of my patterns and hoppings and everything, all that. I think, it's probably very difficult for you to really catch up.
So let me ask you this. Is the subtext of your question, is hopping a valid defense against wireless attacks?
Keep on hopping, keep on randomizing everything you could imagine.
So that's actually a pretty interesting point, because one of the things that makes classic Bluetooth really hard to follow is that the hop pattern depends on a lot more than just a hop increment and stuff like that. It depends on the addresses of the device. So yeah, making more complex hopping sequences makes it harder to do this type of stuff, but I don't think you should treat hopping as a defense against security. You should use a real key exchange protocol, and yeah, who would have known? Yeah, and the encryption protocol is not actually broken. I just figured I'd put these back up if anyone wants to copy them down. And if anybody would like to see any kind of demo, I can show you offline after the talk in a nice controlled environment, not on the spot. Okay, any other questions? Thank you very much.